Okay, so we're happy to have Antoni Rangachev, and he's going to tell us about rational powers of ideals and Hölder continuity.
Okay, thank you very much for the very nice invitation. Um, so I'm going to talk about something rather classical in nature, rational powers of ideals, and I'll try to apply it to the study of singularities. So this is an overview of the talk. First, I'm going to talk about integral closure rational powers. These are concepts that you're all familiar with. Then I'm going to explain the connection between analytic inequalities and integral closure of ideals. This is also rather classical. It goes back to Hironaka and Tessier. And then I'm going to introduce the sheaf of Hölder continuous meromorphic functions. And of course, when we talk about Hölder, this is always with respect to some exponent. And then I'm going to talk about applications in equisingularity of curves. And I'll give a general overview of equisingularity, and I will focus on curves if I have enough time. So, well, here is a definition of the integral closure of an ideal that we know very well. So now what I'm going to do next is I'm going to assume just for convenience that we work over Newtonian domain. And throughout the talk, whenever I consider rings, there will be reduced and equidimensional in the applications of finite type over a field, over the complex numbers, in fact. So here we have a Newtonian domain, and when we want to study the integral closure of an idea, we usually consider the Riesz algebra, which is contained in the polynomial algebra over R in one variable. And by this notation, R of I bar, I'm going to denote the integral closure of the Riesz algebra in the polynomial ring. So it might be a bit confusing because this notation usually indicates the total integral closure, the integral closure in the fraction field of the Riesz algebra. Yeah, I just take the integral closure in the polynomial ring. And so then I consider this quotient of algebras, okay? I can look at, now I consider this quotient as a module over this integral closure of the Riesz algebra. Of course, this is very far from being a finitely generated module, but nevertheless, this set turns out to be finite. Moreover, each associated prime in this set is of height 1. And then one can consider the various localizations at these height 1 prime ideals. These are DVRs. And one can prove that the integral closure of the Riesz algebra in the polynomial ring is equal to this intersection of these finitely many evaluations with the polynomial ring in one variable. So there are various ways to get to the integral closure of the powers of the ideal I. So this is one way that I prefer. So of course, I didn't write here just to save some space, but this integral closure is it's a graded ring, and all the integral closures of the powers of the ideal I appear as graded pieces. Okay. So of course, this construction avoids taking the integral closure of the ground ring, so that's why it's preferred. Okay, so now we can look at the contractions of these valuations to the fraction field of R. And then just by considerations of grading, we get Ries's result, namely that for a Noetherian domain and a non-zero ideal in it, each integral closure of a power of the ideal can be given in this way. Can be as the intersection of all the extensions of the power of n through the various valuation rings, and all this intersected with R. And the associated valuations with these discrete valuation rings are called the Ries valuations. Okay, so this is fairly classical. So then we have the notion of rational powers. So I thought that this notion is introduced by Tessier and Jalabert to study the Lojashevich inequality. So they have famous notes on the integral closures of ideals, where this notion is defined. But recently I learned from a paper of Jonathan Montano and collaborators that in fact Ries and Samuel considered these powers in the 50s, but maybe they did not have applications in mind. Well, a good reference, very concise reference for rational powers of ideals is Swanson and Huneke's book. It appears in section 10. There is a couple of pages devoted to the subject, and there is everything you want to know. It's there. So in particular, I listed three properties that will be needed. So if alpha is smaller than beta, then I sub beta is contained in I sub alpha. Each one of these ideas is integrally closed. Then yeah, if alpha is a natural number, then the n rational power just coincides with the integral closure of the n power of the ideal. And there is a nice expression of these rational powers in terms of Ries valuation. So we're basically looking for elements that satisfy this inequality. Okay. So there is a very elementary proposition about rational powers of ideals, but as you see that it has a surprising application. And I guess this is one of the very few instances where the finiteness of the Ries valuation actually appears as something important. Usually we use Ries valuations to check integral dependence, but the finiteness property is rarely used. But here it's an instance where it's crucial that we have finitely many valuations. So we have a common denominator for all these rational powers, and it's given by the least common multiple of the Ries valuations of the ideal. And well, I give the classical proof of this fact. I don't know, maybe I can skip this, I can continue. I think Dale told me that this first part should be more pedagogical for graduate students. But so anyway, let me say a few words about this. So yeah, so E is the least common multiple. So we want to realize every rational power as n over E, where n is the ceiling of E alpha. So of course, because this is the ceiling function, n over E is greater or equal than alpha. So we have by the first property, we have the corresponding inclusion. And so to prove the opposite inclusion, we apply I guess the third property, which involves the inequalities with the Ries valuation. So, okay, I guess I will skip that. This is something that we all know. Okay, so now a trivial corollary, of course, is that all rational powers between 0 and 1 are of this form. Okay, so we have this common denominator, and we look at the numerator just less than or equal than this common denominator. And the two extreme cases are the integral closure of the ideal and the radical of the ideal. So now let's go to inequalities. So this is all we needed from commutative algebra for now. So now let's go to the complex analytic side, and let's recall Riemann's extension theorem. So here X is now a reduced complex analytic variety, and so we consider a nowhere dense subset of X. So we say that a holomorphic function in the complement of M is bounded near M if for all points in M there exists a neighborhood of that point such that the function is bounded in that neighborhood away from M. Okay, so there are no blow-ups happening here as we approach these points of M. And usually M is taken to be the singular locus of X. So there is this classical, very classical result, which appears in most books on complex analytic geometry or the books of Grauert and Remer on coherent analytic sheaves, or Narasimhan's book. So yeah, there are various references, but so I mean, the proof of this this Riemann extension theorem is rather classical, and it's okay. So I'll say a few words about it, but first let me state the theorem. So if so, these two properties are equivalent. X is locally bounded near M, and X has a meromorphic extension such that this extension belongs to the integral closure, or to the normalization, I'm sorry, to the normalization of the structure sheaf. Yeah, so usually the way this theorem is proved is first it's proved for domains in Cn, and this is this result then in this generality the result is derived from the Cauchy integral formula easily. And then what one does is one realizes X as a covering space of a smooth analytic variety, and well, there is kind of a primitive element theorem, so that allows one to deduce the general case from this situation. Okay, so this is a result of Tessier and Jalabert. So there is an equivalence of, so there are three equivalent ways to say when an element is in the integral closure of an ideal. So again, we work over the complex, in the complex analytic setting. So we have that F is in the integral closure of the ideal I, if and only if F is bounded by the maximum of the modulus of each GIX. So where this maximum takes place in some neighborhood of the origin, and the constant depends on that neighborhood. And there is a nice curve criterion or valuative criterion. So we can check. It says that we can check integral dependence on arcs. And in fact, one can say what kind of arcs we need to check it. And in fact, there are finitely many arcs. This is very much related to the finiteness of the risk valuations. But in practice, you don't know how to construct these arcs, so you have to check for all arcs. And what is the connection here? What is the connection here between this theorem and the previous theorem? So it is not so obvious. One needs to do some work, but yeah, so one needs to principalize this ideal I in order to use the Riemann extension theorem that I mentioned before. So one considers the blow up of I. In fact, the normalization is not really necessary here. So one covers the blow up with some open sets such that the pullback of the ideal is generated by one of the generators at each of each of these open sets, and then one considers the quotient of f by a generator at each such open set, and one invokes the previous theorem to get integral closure relations, which then by some analysis one deduces that this in fact gives an integral dependence relation for f over the ideal I. And so let me say a few words about these curves phi. These curves phi, their pullback on the level of the normalized blowup needs to be, so you need to consider finitely many such curves that are transverse to the irreducible components of the exceptional divisor of the normalized blowup. That's but of course nobody wants to compute this normalized blowup, and so we just check by looking at random arcs. Okay, so now I'm sorry, I'm moving stuff around here. Okay. Now consider again X reduced complex analytic variety. And now the question is what's in between the structure sheaf and its normalization? Are there meaningful objects? And the answer is yes. I guess this was first realized by Zariski in his studies on equisingularity. But in a more crystallized form, this was realized by Pham and Tessier in the late 60s. So they consider this idea. So we look at the tensor product of the normalization over C, and we look at the map to the tensor product of the two normalizations over O of X as OX modules. So this map has a kernel, and this is how we visualize this kernel in terms of coordinates. So if we look at the ring of functions of x at 0 as this quotient ring, polynomial ring modulo I sub x, and we do the same thing about for the normalization. Then we can look at the ZIs, the images of the ZIs in the normalization, and there will be some polynomials of T1 to Tm. So this diagonal, the ideal of the diagonal is precisely of this form. It is equal to Zi of the T variables minus Zi of the U variables. So here one uses the T variables for one copy of the normalization of X and the UI variables for the other copy of the normalization. Okay. And so the Lipschitz saturation of the structure sheaf. So these are all meromorphic functions. These are all meromorphic or locally bounded meromorphic functions, if you wish, or weakly holomorphic functions. It's another name. Such that f tensor 1 minus 1 tensor f belongs to the integral closure of this ideal. And so this is the algebraic definition, but if you turn this definition of integral dependence in terms of inequality, so you realize that this is precisely the condition for that's picking up out of all these locally bounded meromorphic function, it's picking precisely those that are Lipschitz continuous. Okay. And yeah, as I wrote here, indeed, this the Lipschitz inequality translates to this algebraic condition by the result that we just stated, the equivalence of inequalities in integral dependence. And I'm going to denote so the structure sheaf we denote by, so let me remind you here so we're going to use this S for the saturation, which stands for saturation. And well, the corresponding space we're going to denote by XS. And in between X sub S, the XS, the Lipschitz saturation and the normalization, there is the semi-normalization. Okay, so this is the Lipschitz saturation we obtained by considering all Lipschitz meromorphic functions. The semi-normalization is obtained by considering continuous meromorphic functions, just continuous. And now, yeah, there is an important remark here that these objects, because they're given by just extending the structure sheaf with the appropriate continuous functions in the case of Lipschitz saturation with the Lipschitz function, in the case of the semi-normalization with just with the continuous functions. So by definition, there is a well, with the case of the Lipschitz saturation, there is a bi-Lipschitz homomorphism between the saturation and X. And with the case with the semi-normalization, it is a homomorphism. It's just a homomorphism for now. We'll see that it's not just a homomorphism, but it's about, this is about to come. And so why is this the case? So the projection map from XS to X0, this is easy to verify that this is Lipschitz. It's because all these functions, the GIs, they're holomorphic functions on XS. And there is a section from X to XS given by extending the maximal, the elements of the maximal ideal by these Lipschitz continuous functions. So this is how one sees that these two are by Lipschitz equivalent, just by definition. So now the question is, what is in between the Lipschitz saturation and the semi-normalization? And of course, the natural guess, just by anyone who studied calculus, will be, well, you know, the set of Hölder functions, in fact, is more general than just the set of Lipschitz functions. And yeah, one can ask the question. So can we study the set of alpha Hölder continuous functions? And in fact, we can, and this inequality, as we saw in the case of the Lipschitz saturation, alpha equals 1, this is an integral closure condition with respect to this ideal I of this diagonal that we mentioned before. And in the case of when we have an exponent alpha, well, for now, alpha is a rational number. So this inequality, in fact, translates into a condition of a condition on a rational power of the ideal alpha, of the ideal I. Okay, so we define the Hölder saturation as all elements um, in the normalization such that f tensor 1 minus 1 tensor f is in the alpha Hölder power of I. Okay. So one can observe that, well, trivially for alpha equal 1, we obtain the Lipschitz saturation. And as we discussed before, if alpha is sufficiently close to 0, exactly close to 0. So for example, 1 divided by the least common multiple of all these reevaluations, we obtain the radical of I. And this is very important because the radical of I, in fact, corresponds to all continuous meromorphic functions. So this is how we get the semi-normalization. We get it through the radical. I think it's an observation of Bombieri. This is a very old observation. Not in this form, but they study this semi-normalization in regard to some moduli problems. And as it is the case with Lipschitz saturation, just by definition, the alpha Hölder space that we get by looking at the analytic spectrum of OX of the Hölder saturation algebra, this is bi-alpha Hölder homomorphic to the underlying germ. So I'm not going to talk in details about this construction in the global setting, but this construction globalizes. And it follows essentially from the coherence. So the fact that you get a coherent Hölder saturation follows from essentially from the coherence of the normalization. There is no surprise here. So the hard theorem is the Occas theorem, which of course we have. Yeah, so everything else then it's rather trivial to get. So now let me recall an argument from analysis. So far we only considered rational exponents. And so if we look from the perspective of the rational powers of ideals, we can consider rational powers that are greater than 1. There is no obstruction there. But from the point of view of continuous functions on a complex analytic space, the interesting Hölder continuous functions are those with exponent between 0 and 1. And this is rather classical. We know the result for the interval, how we prove that if we have an alpha Hölder function on a closed interval, and alpha is greater than 1, then the function is constant. So this argument generalizes here trivially. So the first case to consider is when we work with essentially with a germ with a smooth germ, and there is the real argument actually works here. We're just subdividing a segment in a smaller and smaller pieces, and we're making use of the triangle inequality and the fact that when alpha is greater than 1, that n to the 1 minus alpha will go to 0 as n goes to infinity. And if yeah, so this is valid locally at the smooth point. Now, so we have to use the fact that on a complex and it's a reduced complex analytic variety, of course, the singular locus is nowhere dense. So, and because we are working with a continuous function, we can approach each singular point through smooth points. And if the function is locally constant at each of these points. So one deduces the constancy of the function everywhere on X. So the conclusion is that only real numbers between 0 and 1 matter. But a little observation, in fact, shows more. So each real number can be trapped by two two rational numbers for which essentially for which the rational power of the ideal that we consider are the same. And so from this, it follows that all the exponents that really matter are these finitely many rational numbers between 0 and 1, these distinguished rational numbers that give us all the Hölder saturations. And anything in between is equal to, so for any two such points, everything in between is equal to one of the endpoints of the interval. And of course, for the first alpha one, or I'm sorry, for the smallest alpha one gets the semi-normalization. So here is the observation, simple observation, that if we have a bimeromorphic continuous map between two reduced complex analytic varieties, then in fact this map is bi-α-Hölder for some rational alpha between 0 and 1. So these bimeromorphic continuous maps that we are familiar with, for example, from the easiest example to consider is the normalization of an analytically reducible singularity, curve singularity, just a branch. Then this map is in fact α-Hölder continuous. And so now, of course, we would like to know if we can compute these alphas for the semi-normalization, not only for the semi-normalization, but in general. Yeah, we would like to give some meanings of this behind these alphas. So the easiest class to consider of analytic varieties is curves. And I'm going to talk about this now because it is also the class where we can explicitly compute these α-Hölder saturations. So there is an observation that goes back to Pham and Tessier, is that if one has a curve in Cn, one can consider, so a germ of a curve in Cn, one can consider a generic linear projection of this curve to the plane. Well, I think, yeah, I used, I guess there is a typo here. I used for the projection to Cm, but in fact, what I am interested in C2. Yeah, okay, so if the kernel of this projection avoids the fifth Whitney cone, this is some generic condition. So if the kernel, I'm sorry, is just the origin, then this is a generic linear projection, and then the saturation, the Lipschitz saturation of the curve and of the plane projection are isomorphic. So by this observation, Pham and Tessier reduced the problem of computing the Lipschitz saturation to a problem of computing the Lipschitz saturation of a plane curve singularity. And this has mostly theoretical significance because, of course, in practice, it's very hard to compute the equations of the images of these projections. So now we can make some observations from this initial properties of the rational powers of ideas that I mentioned. And the key one is that they're integrally closed, these rational powers. And so playing with this property, we can see that yeah, so that the alpha-Hölder saturation of X is the same as the alpha-Hölder saturation of the Lipschitz saturation. And so we can adapt the Tessier-Pham result to this to the more general setting of alpha-Hölder saturations, and then again reduce the problem of computing the alpha-Hölder saturation to that of a plane projection. So this is important that we can consider instead of the alpha-Hölder saturation of X, we can consider the alpha-Hölder saturation of the Lipschitz saturation. So if you think of in terms of sheaves, this is the first sheaf after the structure sheaf. So it's the structure sheaf, then it's the Lipschitz saturation, and then then you have all the Hölder saturations up until you reach the semi-normalization. So one can see that Lipschitz saturation is storied. So that's why it's nice to reduce the problem to computing the alpha-Hölder saturation of a toric curve. And this mostly follows, I mean, there are several ways to do this, but if you think about now, again, the plane curve case, so we know that we can just compute the saturation of a plane curve, and the curve is parametrized in this way. This is with the betas are the characteristic exponents, and the EIs are the GCDs that are defined through these characteristic exponents. Then to determine those elements that are in the Lipschitz saturation, that are in the integral closure of this ideal, one can use the evaluative criterion of integral dependence. And so if you consider a series like that, ft minus fu, and you want to compare its order with respect to the order of these two generators of the ideal, so there is some sort of there is first what's called an inversion formula that you do in order to put this yt minus yu series in powers, these beta zeros to be greater than n. You can assume that. And then the curves that become very interesting are those that for which the Tn minus Un blows up, or so goes to zero, or T is equal to n root of unity times U. And then it's very easy. So when you plug in, so we have this expression for y. But when you act with a root of n root of unity, when you change t with an n root of unity, and when you take the difference, so we know, because there is some Galois action involved here, we know what actually happens in that difference. And in that difference, you have precisely t to the powers of beta I, for example. So you get all the characteristic exponents of in the Lipschitz saturation. So again, so this is a key property that I mentioned before, so that the alpha-Hölder saturation of the Lipschitz saturation is the same thing as the alpha-Hölder saturation of X, and so we reduce the problem to compute the semigroup of a well, okay, so we are giving a Lipschitz saturated numeric of semigroup, and they're a very specific type, and we want to compute this saturation of this semigroup, gamma alpha, the semigroup that corresponds to X alpha. And so this the Lipschitz saturated groups are, as I mentioned before, you get all the betas, but you also get, so E0 is beta 0, E1 is the GCD of beta 1 and beta 0, and you get beta 1 plus O multiples of E1 in that semigroup. gamma, and so on. And beta j is the largest one. From there on, it's the conductor, essentially. From there on, you get everything. Yeah, so then with this in mind, it is not so hard to compute the alpha-Hölder saturation of an irreducible curve. So it is just this picture that we have for the Lipschitz saturation, but we have some translation by alpha. So here is a proposition. So we have that natural number is in gamma alpha. That's the numerical semi-group of the alpha-Hölder saturation of an irreducible curve. If and only if there exists EI that divides P, and if P is greater or equal than alpha times beta I. Okay, so that's the condition. So now let's apply this this proposition to the case of the normalization. So now we ask the question: when do we get, for which alpha do we get of a curve? For which alpha do we get the normalization? And this is analytically reducible curve, so the normalization coincides with the semi-normalization here. And the answer is that it's beta j. It's the greatest characteristic exponent. 1 over beta j does the job. And the reason is that you want t, or 1, the 1 to belong to this gamma alpha. So you apply the previous proposition with p equals 1. Okay, but so E sub y divides 1 only if I is equal to j. So this is precisely corresponds to the fact that the GCD of all the betas is equal to 1. And then the condition 1 greater or equal than alpha beta j is, yeah, so it gives you the bound that alpha is less than or equal than 1 over beta j. So we have, at least for the case of, of curves, we have very good understanding the continuity of the map obtained from the normalization map. Yeah, the continuity of the normalization map of an analytically reducible curve. We know what precisely exponent, what alpha-Hölder exponent corresponds to. And here is an example. So if you consider this cusp, so the semi-group appears on the first row. So then the Lipschitz saturation, you start adding more elements, for example, 8, 11, and so on. So by the way, the Lipschitz saturation always preserves the multiplicity. So for alpha greater than 5/7, so one can compute that the alpha-Hölder saturation is isomorphic to X. So for smaller alpha, we get from 4/7 to 5/7, we get, for example, we get 5. Then the other 3 interesting ranges. So we get more and more elements, and for alpha less than 1 over 7, we get t, or we get the first power of t, we get the semi-normalization. Okay. So let me illustrate this with another example. So suppose you are given. So this is the idea that I'm alluding here to is that at least for curves, continuity always is some sort of a stronger continuity. It's not just a simple continuity. So, and this is illustrated by this simple example. So consider two reduced and irreducible curves in Pn. And so suppose that one of these curves has analytically reducible singularities, and that exists a homomorphism from X to Y. So then the claim is that there exists, in fact, a bi-α-Hölder homomorphism from X to Y for some rational number alpha. And well, the reasoning is trivial. So because of this homomorphism, the two curves have the same Euler characteristic. And one can check that also the homomorphism imposes that Y has also analytically irreducible singularities. I mean, there is no way around it. So now we compare the Euler characteristics of the curves and their normalizations, and there is a classical formula. There is a correction term that comes from the number of branches at the singular points. But because these curves have irreducible singularities, there is no contribution. So the Euler characteristics of the normalizations are the same, and therefore the two normalized curves have the same. So the genus of X bar is equal to the genus of Y bar. But this correspond to Riemann surfaces with the same genus, so there is a diffeomorphism between them. And now, how do we get the alpha-Hölder homomorphism? Well, each normalization, if we consider the normalizations of the two curves, these are, because the curves have analytically reducible singularities, these normalizations are in fact semi-normalizations, and so therefore they are alpha-Hölder. So one can take alpha to be the minimum of with respect to all the singularities. So this taking the common alpha really depends on what happens on the individual singularities. But there is a such rational number that does all the job for all these singularities, and then this composition of these three maps is bi-α-Hölder continuous map. Okay. So I want to say a few words about the motivation of this Hölder continuity. So there is, in singularity theory, there is a big kind of a research trend. There is a branch of singularity theory called metric geometry. And it's been developing quite rapidly over the past 10, 15 years. So this is the branch of singularities theory that studies metric properties of complex analytic and real analytic singularities and tries to deduce, of course, something about the topology and the geometry of the underlying singularity. So there are two motivational results that I want to mention. One is an old theorem by Mumford that says that the topologically irregular surface in C3 with an isolated singularity is smooth, and topologically means that there is an open neighborhood around the singularity that's homeomorphic to an open ball. So, and then there is a more recent result from I guess 10 years ago, that Lipschitz regular points of a complex algebraic set are smooth. So Lipschitz regular means, again, then there is an open neighborhood around the point that is by Lipschitz homomorphic to an open ball. So I just want to mention this just to indicate that Lipschitz continuity is a very strong property. You see that if one just requires homomorphism, the only examples that actually work is what Mumford did. These are topological. This is for essentially for normal surfaces in C3. But in general, this fails. I mean, it fails for curves, it fails for higher dimensional varieties, but the Lipschitz condition is rather strong. So now, in what follows, I'm going to talk about families of curves, and I'm going to propose this notion of alpha-Hölder equisingularity as a unifying notion of several familiar notions of equisingularity. And of course, the first case one should do is the case of curves. But this, what I'm going to say now about equisingularity actually applies to families of varieties of arbitrary positive dimension. So what is the usual family setup when we consider curves? So we consider a flat embedded deformation of a reduced curve. Usually the parameter space is assumed to be smooth. And it's convenient in complex analytic geometry, especially when one studies the topology of such objects, is to embed the central fiber of the family into an open ball and to view the entire family as a analytic subset of the ball times the parameter space. So each fiber is contained in this ball. So this kind of things we can do in analytic geometry, not in algebraic geometry. So, but this is very important because, well, for several reasons, but it gives you some sort of compactness. So one of the key tools that we like to apply is this Ehresmann fibration theorem, for which you need compactness. And to get compactness, that's what you do. You make sure that all the fibers are contained in some fixed in a bow of some fixed radius. And so one chooses this bow usually in such a way so that when we talk about curves, so we have a families of isolated singularities. So one chooses the bow so that it contains only the origin, and that the boundary of this bow is transverse to so intersects the central fiber at smooth points transversely. And in fact, this property propagates to nearby fibers by openness of transversality. So, so this is what I describe as a family setup, but very often there is a family setup with a section, and this is a typical setup that comes from stratifications for example, Whitney stratification. So when we consider pairs of strata and one of the strata is contained in the closure of the other strata, there is a question. I'm sorry. Sorry, what did I do?
That's okay. Don't worry about it. I was just wondering if we wanted to take any break anytime soon.
Yeah, I'm fine with this, but yeah.
If you want to get to a better stopping point, that's fine. But I just wanted to
So it's been like what, 1 hour or
almost an hour, yeah.
almost an hour?
Yeah.
Um, let me see. I have well, maybe we can have a 2-minute break and then I will finish with this. Is that okay? Or you want like 5 minutes or?
Probably 2 minutes, fine.
Okay, just a water break. All right, so very often there is this family setup that arises from stratifications. So so this setup, the parameter space, that there is a section from the parameter space to the total space of the family. Okay, and so we can do some reparametrization tricks to ensure that in fact the points of the parameter space trace the origin in each Cn. So the total space is in Cn times Ck, and we can make sure that because Y is smooth, that in fact the points of Y are identified with the origin in Cn. So here is the definition of topological equisingularity for a family of flat family of curves. So we say that the family is topologically equisingular if the total space can be factored as a product of the central fiber times the parameter space, and there is a homomorphism between the total space and this factorization. So it is not so obvious why it's a topological result, that in fact this is also equivalent to insisting that to asking that there is a homomorphism of pairs. So a homomorphism, so that open ball that we consider in the very beginning, where each fiber lives. So it's a homomorphism of the ball into itself that maps x0 to xy. So this is for curves, this is equivalent. In general, this condition is stronger than just topological equisingularity. This is embedded topological equisingularity. And Whitney equisingularity for curves, so this is perhaps the best studied equisingularity. I have to say that maybe a good reference for it is Lippmann's overview of equisingularity. So there's a lot about Whitney equisingularity there. It's also called differential equisingularity. So it's been studied quite extensively, but I don't want to give the general definition. So for curves, when we specialize to curves, so this is something stronger than just topological equisingularity. We want a constancy of the multiplicity along y. So this is a setup where we have a section from y to x. So along the points of y, we want constancy of the multiplicity. So it's a result of Le and Tessier that Whitney equisingularity is a topological triviality not only of the family, but of all the plane slices that pass through the parameter space y. So there is a number of families to consider. And so Whitney equisingularity is equivalent to the topological triviality of all these families. And of course, for singularities, we don't have a Lefschetz hyperplane theorem. So all these slices, plane slices, in fact, they give some non-trivial information. And we have a notion of strong simultaneous resolution. So for this, we just require that the normalization morphism induces a normalization of each fiber, and the strong part. So this is what's called weak simultaneous resolution. The strong simultaneous resolution is if the inverse image of y, again, here again we are in the setup with a section. So the perimeter space is in X. So there is a section from the perimeter space in X. And so the inverse image of that is locally analytically trivial. So that's quite strong. And for alpha-Hölder equisingularity, one can naturally introduce it by saying that we want a factorization. So here we have the open ball times y. So this is our ambient space. So we have this factorization of pairs. So we want that there is this factorization is given by a bi-α-Hölder homomorphism. Okay, so that the total space factors as a product of the special fiber times the parameter space. And so when alpha is equal to 1, this is called Lipschitz equisingularity. It's a notion that's been studied quite well. So the first question that we can ask is, can we find fiber-wise numerical invariants that control these equisingularity conditions? And this was done in full generality for the case of topological equisingularity, Whitney equisingularity, and strong simultaneous resolution for families of curves. In a recent paper that's available on the archive, it's called The Complete Intersection Discrepancy of a Curve 2, Families of Curves. So this is with Bengush, Lanier, and Gaffney. And it relies, so the algebraic machinery for this paper was developed in the complete intersection discrepancy of a curve 1, numerical invariance. So in both papers, I just want to mention something, to add something briefly. It turns out that in order to study arbitrary families of curves, it's, well, our approach is rather different than previous approaches. We take the approach of the relative Nash blowup and the relative conormal space. And both of these geometric objects, one can define them, one can have good control on them if one embeds the curve in a complete intersection curve, or the families of curves in a complete intersection family. And this naturally leads to linkage. So some basic linkage was applied to the development of this new approach. So now let me explain what the invariants are. The invariants are quite old. They're well known. So let's consider for each of these fibers, let's consider, well, locally at the origin, let's consider the normalization map. So we have the number of branches at that point. So we can define also the delta invariant. There is some problem with LaTeX here. So this is the push forward of the normalization. Yeah, I don't think it looks nice here. It was displayed nice here. Anyway, so that's the delta invariant. And the Milnor number, it's 2 delta minus the number of branches plus 1. And so this is for each fiber. And by m sub y, we define the multiplicity of x sub y at 0. And so the first theorem reads as follows. So the following are equivalent. So these functions, the Milnor number and the multiplicity, are constant across y. So each fiber has only one singular point, and that's the origin. So this constancy of this invariance implies non-splitting of the singular locus. And the family is Whitney equisingular. And this is also equivalent to strong simultaneous resolution. So I have to say that so for one parameter families, the equivalence of 1 and 2 was known there's a result of Briançon, Gallego, and Rangechev, which built on results of Buchweitz and Groyle. But all this machinery developed by cohomological machinery developed by Buchweitz and Groyle is valid only for one parameter families of curves. They need the central fiber to be a divisor. And up until now, this was an obstacle that could not be overcome. And yeah, so for one parameter families, the equivalence of 1 and 2 was known, and the equivalence of 2 and 3 was known, of one direction was known for plane curves, and the other one in general, but I forgot which one was it. These are results by Tessier, but one direction was just for plane curves, families of plane curves. Okay, and then there is another result that characterizes topological equisingularity in terms of the constancy of the Milnor number. So here we have the total Milnor number, which is just the sum of the Milnor numbers at all singular points of the fiber. And so if this is constant, then, so I mean, there are some assumptions that are needed in order to prove topological triviality. And they come from the fact that the central fiber, it's just a germ, it's contractible. Okay, and so you cannot have the nearby fiber have multiple components intersecting at different points. You cannot. There is no way to get a homomorphism. So you require that all the irreducible components of the nearby fibers meet at a single point. Then the family is topologically equisingular, and if the family is topologically equisingular, then the Milnor number is constant. So the crucial technical ingredient here in this result was the Zariski upper semi-continuity of the Milnor number. Again, this was not known before. So we proved this with, in fact, finding a formula. It's called a Legge-Royal-Tessier type formula for the Milnor number, which relates it to multiplicities. And multiplicities can be realized as intersection numbers, and intersection numbers have nice properties, generic properties in families. One can prove using generic flatness and results like that. One can prove generic constancy. And so with the help of some Morse theory and some topology, we got the Zariski upper semi-continuity of the Milnor number, and that's the central ingredient in this result. And so here I have just some pictures. Wow, this is a very, very equisingular family. These two parabolas touching each other. So of course here we have constancy of the delta invariant. It's just the intersection multiplicity of the two branches. So here everything, of course, this is maybe even analytically equisingular. And of course, the singularity theorist's favorite example is the node degenerating into a cusp. So this is not an equisingular family. We have, so the delta invariant, well, it has weak it has a weak equiresolution. So one can resolve all the singularities by the normalizing the total space. But that's about it. So even topological equisingularity fails because the number of branches is not constant. So the nearby branch is reducible, and the special fiber is irreducible. So there is no way that this can be a topologically equisingular family. So the general relation of the different equisingularity notions that are the most common is summarized in this figure. I want to say a few words about it. So we have Lipschitz equisingularity. So we require that there is some trivialization of the family by Lipschitz homomorphisms. So that implies Whitney equisingularity. This is not a trivial result, but it's known. And Whitney equisingularity is not just a topological equisingularity, it requires topological equisingularity of the plane slices that pass through the parameter space. So it's a strong form of topological equisingularity. So now, for us, it's quite important to understand what is, well, if we can get these three conditions, we can unify them kind of can get them as instances of one equisingularity condition, namely of alpha-Hölder equisingularity. So, of course, Lipschitz is the same as alpha equals 1 Hölder equisingularity. Of course, alpha-Hölder implies topological equisingularity. So, in fact, what we are able to see in the case of curves, that topological equisingularity implies alpha-Hölder equisingularity for some alpha. So it is believed that Whitney equisingularity will give alpha-Hölder equisingularity for some alpha, that one can find bounds on alpha in the case of complex analytic varieties, not real analytic varieties. There it's, well, it's harder, we don't know. And then there are other notions of equisingularity. Then there is a risky equisingularity, which is a notion developed for hypersurfaces, which is very much related to weak equiresolution. So some sort of a resolution, simultaneous resolution modulo some phase changes. So the equivalence of Lipschitz and Zariski, in fact, this is an equivalence here. It's in dimension 1 and 2. It's known. So for families of curves and surfaces, so plane curves and surfaces in C3, these are recent results of Parushinsky and Paunescu, and Neumann and Pichon. And so finally, I want to conclude with uh, uh, this. It's kind of a easy observation from our work that I mentioned before, that if we have a topologically equisingular family, then it's a bi-α-Hölder equisingular. So remember that there was this example with the two projective curves. So it's in fact quite similar. What I'm going to say here, it's quite similar to what I described there. So topological equisingularity implies um, constant Milnor number, which implies that the delta invariant is constant and the number of branches is constant. So here we have some distinguished points. So the family, so we have a family of curves, and each fiber, the irreducible components meet at some distinguished points, and these points are parametrized by an irreducible component of the relative singular locus, which is, in fact, one can show that it has to be smooth because it is of degree 1 over the parameter space. So it's an application of the Weierstrass preparation theorem. So there is this distinguished component of the relative singular locus that parameterizes all these singular points where we have actually a number of branches greater than 1. Okay, so and this number is constant. So one can see this from the constancy of the Milnor number, which follows from the assumption of topological equisingularity. And because of the constancy of the delta invariant, we have that, well, so we have on the level of the total space, we have R number of components, and on the level of the fibers, we have the same number of components. This is where the constancy of the local branches plays a role. And so one reduces the problem to considering just curves, families of irreducible curves. So this is this xj's is irreducible, and we have the normalization. So this is homeomorphism because each individual fiber is locally analytically irreducible. The normalization map yields resolution. Well, yeah, the normalization of xj is smooth. But there is one thing that I want to mention here. So even if the family is flat with reduced fibers, if you consider the induced families on the level of the components, the irreducible components of X, so these families might have, if you look at the special fibers of these families, they might have embedded components. So when one considers the normalization and the fibers of the normalization, one should be careful not to consider the normalization of the fiber because that thing is non-reduced. It's generically reduced, but it might have embedded component. So okay, nevertheless, so we have a homomorphism, fiber-wise homomorphism from the normalization of xj, the fiber over y to the fiber of xj over y. And so what we have to consider, so we have for these families, we have two types of curve. We have the special one and we have the nearby one. And we want to get alpha-Hölder homomorphism because again this homomorphism it is a semi-normalization homomorphism, so therefore it's alpha-Hölder, and so one has to take the greater exponent beta j exponent of these curves, and one divided by the maximum of these exponents gives you the desired alpha-Hölder um, 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 continuity. And I think that's all.
All right. Thank you, Antoni.
Thank you.
Any questions?
Tony, your results, the new results you talked about, they're basically all for curves. That's correct. No? So is there any, do you have any clue what could happen in higher dimensions?
Yeah. So this is for curves. For higher dimensions, one can well, the only hope that we have is that one can prove that Whitney equisingularity implies alpha Hölder for some alpha.
Nice.
And then bounding this alpha is quite interesting because this trivialization homomorphisms that one gets from the Whitney equisingularity that from like this through these isotopy theorems of Tom matter, they're really of Hölder type. So one needs to, it's mostly analytic geometry. We haven't, I mean, we have an idea how to do it, but we haven't actually spent too much time on it.
Well, thanks. That was a very interesting talk. Very interesting. Thank you.
Okay. Any more questions? Okay, well, thank you again, Antoni, and thank you all for coming.
Thank you.
Thank you. Bye-bye.
Bye-bye.